This is the second electromagnetism video for A-level physics. The aim of this video is to learn how to calculate magnetic flux. Last video we saw that voltage is induced when the amount of field or magnetic flux through a loop changes. Flux is symbolized by the symbol phi, and is directly proportional to the number of field lines passing through a surface. So directly proportional to the number of field lines passing through a loop. And we saw that previously. Flux is really important because the rate at which the flux through a loop changes is directly proportional to the voltage induced in that loop. If the flux changes a lot in a short period of time, the voltage induced is going to be large. If the flux changes by a small amount in a longer period of time, the voltage induced will be small. This is actually what Faraday's law essentially states, and we'll get into that in video 4. Okay, moving on. So we should look at the factors that affect the flux. Factors that affect the flux. One factor we should investigate is the area of the loop. So the area of the loop. To consider this, we'll need to draw a magnetic field and place a loop into that magnetic field. Here we have the magnetic field represented by the evenly spaced red crosses. So crosses again mean that the field is directed straight into the page. There are two loops here referred to as the first and the second. The important difference between them is that their areas differ. So the second is 1.5 times wider and 4 times taller. So the area of the second is 6 times greater than that of the first. So their areas are in a ratio of 1 to 6. Let's also look at the number of field lines they have. So the first has 2 field lines. So we've got 2, and then the second has 12 field lines. If we simplify that ratio, say F for field lines, we get 1 to 6. So the ratio of field lines in these two loops is the same as the ratio of the areas. And the number of field lines is directly proportional to the flux. So therefore, if the area of a loop increases by some factor, the flux must also increase by that factor. The flux and area increase or decrease by the same factor. What we can really conclude from that is that they are directly proportional to each other. So we can say phi, the flux, is directly proportional to the area. Okay, so that's one of the factors that affects the flux through a loop. The other factor to consider is magnetic field strength. magnetic field strength, which we represent with the symbol B. So we're going to need two fields of different strengths, and equal sized loops will be placed in them, one in each field, and we'll compare the flux through them. Here we have two magnetic fields, and in each field there's a loop. The loops are identical to each other. The field on the right is 4 times stronger than the field on the left. We can sort of see this. If we say the separation between field lines for the field on the left is 2 relative units, but bear in mind that affects both the height spacing and the width spacing. And then in the field on the right, the relative spacing is 1, both vertically and horizontally. So the field strength of field 1, I'll call this one, the one on the left, is 4 times that of field 2. Let's then look at the amount of flux passing through, and to do that, the only way we can really do that is look at the number of field lines going through each one. So there are 6 field lines going through 1. So field lines, got 6 going through the first, and then going through the second we've got 4 by 6, 24 field lines passing through that. If we simplify that ratio, it becomes 1 to 4. We should also write down the ratio of magnetic field strengths, so the ratio of field strengths is 1 to 4. So when the field strength is increased by a factor of 4, the number of field lines through the loop, the same area of loop, will increase by a factor of 4 as well. The two of them turn out to be directly proportional to each other, and the number of field lines, that itself is directly proportional to the flux. So we can say that the flux is directly proportional to the magnetic field strength. So you can write phi is directly proportional to B, the magnetic field strength. Okay, we can bring these two ideas together. We've seen these two proportionalities. We've seen that the flux is directly proportional to the area of a loop, and that it's directly proportional to the magnetic field strength. We can take these two together and say it's directly proportional to the product BA. It actually turns out that phi is equal to BA, not just directly proportional to it. This is sort of like going through the GCSE maths process where we take a proportionality, write k in front, so we have phi is equal to kBA, but it turns out, and we're not going to justify it here, but it turns out that k is equal to 1, and so that allows us, well, that means that phi is equal to BA. It's equal to magnetic field strength multiplied by area of the loop.